Probability and Statistics, Hypothesis Testing Part 1. What is a hypothesis? Hypothesis is a guess, in fact. Guess that something is true based on observation and experience. And the difference between a hypothesis and a theory is that the hypothesis is untested, subject to revision and dismissal, while the theory involves something that's been tested repeatedly over time, observable results agreed upon generally by the research community. So let's go through the process. The scientist notes a natural phenomenon and puts forward a hypothesis. So notices, asks a question about researchers, and then puts forward a hypothesis. Thereafter carries out experiments and looks for empirical evidence verified by observation or experience. After the rigorous testing, and that means extreme, thorough, careful, with no empirical evidence found to disprove it, the hypothesis is accepted and advances to the status of a theory and becomes generally accepted. Man-made global warming cannot be called a theory, it's still a hypothesis, as was when Einstein hypothesized that there is a static universe. Just some examples of hypotheses which many think are proven. And here's some other examples of possible hypotheses. And these are ones that could all come up in research. Sort of thing that could come up in research with human beings and with industry. Right, how do we go about performing a hypothesis test? Always two hypotheses. There's the null hypothesis, H0, and the alternative hypothesis, H1. And we weigh them together. The null hypothesis says nothing new is happening and there's no change from the previous situation. Must be stated as a numerical value of the parameter and involves the use of an equal sign. So let's look at a sample problem. Researcher looking at the effects of a radical exercise program on knee surgery patients. Good chance it will improve recovery time, but it may make it worse. Average recovery time for knee surgery, 8.2 weeks. So, first of all, we state that nothing will happen. And that's the null hypothesis. Recovery time will stay at 8 weeks, and therefore we say H0 mu equals 8.2. Now it says nothing is happening. It's stated with a numerical value, and it uses an equal sign. Null hypothesis is like not guilty in courts. I am what is, the default, the status quo. I'm already accepted, can only be rejected. The burden of proof is on the alternative. I am the null hypothesis. Let's look at the alternative hypothesis. It indicates there is a difference. It involves the use of anything but an equal sign, not equal to, less than, or greater. And it is the statement taken if H0, the null hypothesis, is rejected. Oh, the suspense. Right, let's go back to our sample problem. We already have the null hypothesis there. Now we need to figure out the alternative hypothesis, which quite simply is the opposite of the null hypothesis. Not always necessarily, it could be in one direction only. In other words, what happens if our experiment makes a difference? Well, there we are. H1 is not equal to 8.2. Now, usually the experimenters would want it to improve, so they would say mu greater than less than 8.2, so it's lower recovery time, but this is not equal to. Right. There is a difference, it says, and it uses one of those signs, not equal to. All right, spotting the mistake in the H1. If we, in H0 in fact, if we now calculate, for example, all right, that this example at the 95% confidence interval, I hope you've done intervals, that's my previous video in the same series entitled Estimating Population Parameters. So you need to go through that first because this doesn't deal with that in great detail. Right? So there we have the values of x for that the case. We use the z-scores to get there. Means we want a sample mean less than 6.6 to show significantly that the therapy makes it worse. So if it's less than 6.6, because that's what the mean should be by what we have, or greater than 9.8 to show significantly that the therapy improves time. So in other words, it says the null hypothesis status quo there. H1 only works if it shows that in fact at the 95% confidence interval things have changed. And then we'd reject the null hypothesis. Right, so there's the acceptance region between the two z-scores. And there's the rejection area on the sides. That's the z-score corresponding with the degree of confidence, 95 confidence level. We found 1.96, then we used our formula to find it for this particular distribution. This is called the two-tailed test. That's the dog. Yeah, you probably wonder why there's a dog sitting there. It has two tails because you're either looking at less than or above. So when we're doing 95% confidence interval, we need 5% outside, so we take 2.5 on each side. So we've actually taken 97.5. Which gives a z value of 1.96. Right, a sample problem. A horticulturist has a clear indication from his records that the average mass of his fully developed pumpkin is 5.5 kilograms. A nursery company has given him a sample of newly developed liquid fertilizer with a claim that it will increase the average size of his pumpkins. Now you see, if you give them to the fertilizer to them, and the pumpkins end up having an average of 6 kilograms, we need to be able to say, well, is that significant or not? Can we expect that sort of variation? If we can't expect that sort of variation, then we reject the null hypothesis. So he randomly selects 33 seedlings, waters them with the fertilizer until they're fully grown, and records their resultant masses. There's the null hypothesis, that it stays at 5.5, there is no change. H1 greater than 5.5. Now notice now we don't have less than or not equal to, because the specific claim is that we will increase the average size, so we have that. So in fact, this is only one tail on the one side. Work with 95%, but we're no longer dividing the 5% between the two sides. So therefore, if you look at 95, we now have a Z value of 0.45 on the Z table. And we need them to be inside there. So as a summary of steps, set up H0 and H1. The two-tailed test, H0 new equal 25, not equal to 25. There would be examples of two-tailed, and the rejection region is on both sides, and whatever the confidence level is, we're going to halve it. We're going to take, well, the difference we're going to halve. So for example, if we're doing it 99%, then we're going to put a half on each side to make up the 100. If we're doing it 90%, we'll put 5% on each side. So in other words, we would look for the significance level there, that being the case. One-tailed, only there's your critical value. We'd look up the actual specific Z value for the confidence level. And there as well, one-tailed, we'd only look up the Z value, we wouldn't do any halving. Deciding on the level of significance. So 90, 95, establishing the acceptance region, non-region, and the critical or rejection region. And that's where we use our Z table. Select a sample, collect data from the sample, calculate the relevant statistic. In this case, it's the Z score of that sample, using the calculated test statistic to determine if the sample statistic is close to the claim or not close to the claim. Accepting the claim or rejecting the claim.